Today, we're going to dive right into the very first chapter of your Class 10 math syllabus, real numbers. By the end of this, we're going to break it all down so it's super simple for you. So let's get right to it. Why does this chapter even matter? Well, it's pretty simple. Getting this one chapter right can lock in a solid 6 to 8 marks for you in your board exams. It's a fantastic place to start building up a really great score. And honestly, there's absolutely no need to be scared at all. This is one of the easier chapters, trust me. If you just get a handle on the concepts we're about to cover, scoring full marks here is totally achievable. Okay, so to get this right, you've got to start with the basics. Let's do a super quick review of what we're even talking about, the number universe. Think of real numbers like a big family with 2 main branches. On one side, you have your rational numbers. These are the straightforward ones you can write as a simple fraction. And then you have their mysterious cousins, the irrational numbers, like pi or the square root of 2, that just go on forever as decimals without repeating. All right, tool number 1. This is a big one. It's called Euclid's division lemma, but you can just think of it as a really smart division trick. Let's see how it works. Now, this might look complicated, but it's not, I promise. It's basically just a fancy way of writing down long division. But here's the secret, the part you absolutely have to remember. That remainder r must always be less than the divisor b. That little detail is the key to the whole thing. So you're probably thinking, okay, cool formula, but what do I do with it? Well, its biggest use, and I mean, this is a classic exam question, is finding the highest common factor, or HCF, of 2 numbers. This is a big one, so let's break it down. Let's walk through a real example. Finding the HCF of 657 and 306. In step 1, we divide 657 by 306, and we get a remainder of 45. Now here's the trick. For step 2, that old remainder, 45, becomes our new divisor. We just keep doing this little shuffle until, boom, step 4, we hit a remainder of 0. And that's the magic moment. The second you hit a 0 remainder, you stop. The HCF is simply the last number you divided by. In this case, it's 9. See? Not so bad, right? Next up, our second major tool, the fundamental theorem of arithmetic. This sounds super official, but think of it like a secret code or a unique DNA for every single number that isn't a prime. So what's the big idea here? It's actually pretty simple. It just says that any number that isn't a prime number can be broken down into a string of prime numbers multiplied together. And here's the cool part. That string of primes is totally unique to that number. Let's take 60, for example. We can break it down into its prime building blocks. 2 2s, 1 3, and 1 5. That's its unique prime fingerprint. No other number has that exact same combination. So why do we care about this prime code? Well, it makes finding the HCF and LCM super easy. Look at 12 and 18. For the HCF, you look for the prime factors they have in common, and you pick the lowest power. For the LCM, you take all the prime factors from both numbers and pick the highest power for each one. And here's another golden rule. Seriously, write this one down. It's a lifesaver in exams. HCF times LCM always equals the product of the 2 original numbers. You can see it right there with our example. It works out perfectly. 216 on both sides. All right, let's tackle a type of question that pops up all the time. How can you just look at a fraction and know if it's going to be a nice, neat decimal that ends, or one of those messy ones that goes on forever? Believe it or not, there's a really simple trick. It's all about the denominator. If its prime factors are only 2s and 5s, that's it, just those 2. The decimal will terminate. It'll stop. So let's see it in action. we've got 13 over 3,125. Ignore the top, just look at the bottom. 3,125 is just 5 5s multiplied together. Since it's only made of 5s, our rule says, yep, it's a terminating decimal. Okay, but what about 1 over 7? The denominator is 7. Is 7 a 2 or a 5? Nope, so it fails the test. That means this decimal is going to be non-terminating. It'll just keep on repeating forever. Okay, deep breaths. We've arrived at what a lot of students think is the final boss of this chapter. Proving a number is irrational. Specifically, the classic proof for the square root of 2. We're going to solve this like a detective, using a clever method called proof by contradiction. Step 1. We assume the opposite of what we want to prove. Let's pretend root 2 is rational. Now, if we follow the clues from that assumption, we find something weird. We prove that p has to be even, but then, if you follow that clue further, it means q also has to be even. And, wait a minute, that's the contradiction. We started by saying they were coprime, which means they couldn't both be even. Our assumption has led us to a dead end. So what does a detective do when their main theory leads to an impossible situation? They throw it out. Our initial assumption that root 2 is rational must be false. Therefore, the only thing left is the truth. The square root of 2 is irrational. Case closed. And just like that, you filled up your math toolkit. You've got Euclid's algorithm for HCF, prime factorization for HCF and LCM, that super quick decimal test, and the powerful proof by contradiction method. You now have the concepts and the tools to conquer this chapter. The only thing left to do is practice. Remember to show your steps clearly in the exam, and those 6 to 8 marks are totally yours for the taking. You've got this.